You like 3D printers? I love 3D printers. I have 4 of them. 2 FDM, 2 SLA. One's that deposit ink by melting it and printing it, and the other one, the SLA ones, print out of liquid using lasers or UV screens. Now, today I want to talk to you about plasma, combining plasma with 3D printers. So using plasma for additive manufacturing. And this is what this paper is about. So let's dive in. So this work, published in Plasma Processes and Polymers very recently, February 25th, 2020, discusses its a review of use of plasmas in additive manufacturing. And I'll try to go over this review paper pretty quickly, so please feel free to use the link down in the description to get the paper yourself and read it for full details. Additive manufacturing, as this paper suggests, has drastically improved over the last 15 years. It's gone to a big boom, and it's hard to find anyone who does not own or doesn't know someone who owns a 3D printer. Some interesting examples, like this paper mentions, include laser sintering, electron beam melting, extrusion, photopolymerization, and other types of additive manufacturing methods. Now, the problem is it is hard to deposit metal onto polymer surfaces. Metals have very high melting point, making it virtually impossible to additively manufacture metals together with plastics. So in plasma can play an interesting role, whether in directly depositing metals or in post-processing. Now, in post-processing, most commonly temperature is used, and plasma can be alternative to that. So interestingly, as this paper mentioned, and in my own thinking, plasma's biggest advantage may be in the fact that plasmas can achieve effects similar to temperature without the temperature. And plasmas can operate very close to room temperature, or even at room temperature and at room conditions, making them very interesting for thin film deposition, material surface treatment, and other types of applications. Now, suggested in this paper are 2 types of approaches. I can think of a couple more, but this paper suggests 2. Either you create some kind of a suspension, spray it, aerosolize it, pass through plasma, and then deposit, or you use traditional 3D printing type of an approach and then stick it into plasma for later processing. Other possibilities are also available, in my humble opinion, but this paper talks about these 2, and this is the state of the art. Now, the first approach is direct writing using plasmas, and here there are many advantages of microplasmas, really tiny plasmas that have been used extensively for deposition of silver or copper using very many different types of plasmas. So we can deposit metal, which is very challenging usually. Surface functionalization. Plasmas are very good. Here's an example of a small microplasma, multiple microplasmas modifying the surface. So direct writing using plasmas is possible. And this is something you can definitely put on top of a 3D printer. Vapor deposition. You can put through this microplasma, you can put some kind of vapor and deposit it onto surfaces, and this has been demonstrated. See, here's a nice photo of a flexible microplasma stamp or microplasma. Here's a channel with 2 electrodes, one on top, one on bottom, and here's a channel, and we see a photograph of plasma formed inside of the channel depositing some kind of material. So it's very nice. Personally, I don't see much of a difference between vapor deposition and aerosol deposition. The process can be very similar. It's pretty much you have some kind of microplasma through which you pump your precursor. So in this case, they're demonstrating 2 plasma electrodes. One oxidizes the surface, one deposits a polymer onto the surface you want to process. Other application of plasma is combining inkjets with plasma. So you basically have an inkjet generating droplets, passing through a plasma zone, activating those droplets, changing their chemistry, and depositing it onto the processed substrate. And very nice, precise writing has been demonstrated. Keep in mind, this is still two-dimensional, so it's a layer deposition, and we need to do some adjustments to this type of a system to do a true 3D printing. However, this is truly an additive manufacturing. We didn't subtract anything, we didn't cut any parts out, we just deposited a single line. Something similar is electrochemical reduction, where we put plasma on a drum type setup and use it to etch surfaces or deposit onto surfaces, but primarily etch. Very nice deposition onto even flexible substrates. So these are interesting and valuable results. Now, the second scheme that this paper suggests is using plasma for post-processing. Here, it is important to employ large volume, large scale plasmas that are challenging to make uniform at atmospheric conditions. Metal nanoparticles from a suspension were deposited onto different substrates, and the treatment process went only up to maybe 80 Celsius, which is significantly lower than thermal processes involved today that are in hundreds of Celsius, if not above. We can use particle-free precursor inks to deposit similar things using plasma for sintering or melting. And here is an example of silver nanoparticles deposited, printed, inkjet printed onto a glass substrate, and then at different plasma parameters we see fusion of these particles, so melting of these particles using plasma at significantly lower temperatures than thermally. The substrates can be flexible. Nothing stops us from printing conductive patterns onto flexible substrates. And of course we can use carbon-based materials, various carbon nanotubes, graphene-like materials, etc. Metal oxides. So a lot of this type of printing is possible. Again, printing on flexible substrates, why not? Roll-to-roll treatment has been demonstrated, so this can scale up to industrial applications, but this is additive manufacturing, but this is not 3D printing. That is one of the challenges that is addressed later in the paper. Insulators can be directly deposited. For example, boron nitrate deposition has been demonstrated. Now, how do we get to 3D printed fabrication? Well, we can use arrays of these electrodes. We can attach them to a 3D printer. We can make electrodes in multiple dimensions. So it's up to you, the listener, and up to me, the engineer, and up to us, the plasma community, to try to figure out how to make this into a commercial and hopefully even consumer 3D printer. Challenges? The biggest challenges that this manuscript brings up is how to make it 3D. Everything I told you about today is pretty much two-dimensional. It's a single layer. Now 3D printers, they're two-dimensional, 2.5 dimensional. So it's kind of like a 2.5 dimension. However, plasmas have been demonstrated so far mostly in 2 dimensions, not yet even 2.5. So this is a big challenge. Depth of penetration of plasma treatment is another challenge. And maximum so far that has been demonstrated is just a fraction of a micron. So if we want to see, plasma is very famous for its ability to change chemistry. However, changing chemistry in depth is challenging. So is the scale up. Scale up is a big question dielectric barrier discharges have been demonstrated to work on a decent scale, but not microplasmas. They're microplasmas. They're very, very small. Speed of the process, of course, is something that the authors address, and it is inherent in all of the 3D printing technology. It's not that fast, or at least not that fast yet. Now, the big advantage is we have chemistry, and having multiple chemistries is also a disadvantage because it introduces great complexity to what we're trying to achieve, making it a relatively challenging process to add plasma to additive manufacturing. However, we're striving to do this, and conclusion of this paper is very nice. I appreciate it very much. They say that in this relatively short amount of time, I've only been hearing about plasma in additive manufacturing for 3, 4, 5 at the most years. And in this time, there has been pretty significant advancements made. So I, for one, very much look forward to introduction of plasmas into additive manufacturing processes. And I hope you take a read of this paper that I interested you enough in this direction, and let's continue to look at applications of plasmas and other technologies in additive manufacturing.